Here's a very interesting physics question which created some controversy on the internet some time ago. And I just want to present a more analytical way of looking at things. And if you'd like to see anything similar to this in the future, or if you have any suggestions for any topics or specific problems that you'd like to see on the channel, let me know in the comments. Okay? So we're dealing with a helicopter that's flying horizontally at constant speed. Okay, this is key. And attached to the helicopter, there is a flexible uniform cable, as we're being told here. And also, we cannot neglect air friction, right? So in a lot of physics problems, we have this idea that we can just ignore air friction, but not this time, okay? And this is a multiple choice question where we just have to pick what is the shape of the cable as the helicopter is flying horizontally with a constant speed, okay? With a constant velocity, actually. So let's try to first, no. So let's try to draw a free body diagram of the cable first, okay? And without losing any generality, we're going to assume that the cable has some curvature to it, okay? So let's say the cable maybe looks like this, or actually let's draw it something like that, okay? And then we're going to see what shape the cable will actually have based on some of the physical parameters that we're going to be using, okay? So this cable has obviously a mass, so there will be weight acting on it, but most importantly, we're going to define an angle theta, okay? So I'm going to define theta, which is an angle, and the angle theta is this angle. So at any point on the cable, I'm allowed to draw a tangent to that particular location, and the angle between that tangent line and the vertical to that point is what I will call theta from now on, okay? And what I'll then do is I'll just consider a section of that cable, okay? So in other words, I'm going to draw a free body diagram of a section of the cable. And the way in which I'm going to do it is I'll consider the cable from here to here, maybe. So let's draw that on this page. So this is just the section of the cable, and normally it would continue upwards. And let's draw all the forces acting on this cable. So first of all, we have the weight. Okay, which I'm just going to call it mg for now, but we're going to come back to this in a second. Now, also we have the aerodynamic drag. And aerodynamic drag will act horizontally to the left. Okay, let's just call it drag for now. And the reason is because aerodynamic drag always opposes the velocity. Okay, so if the velocity is this way, then drag is this way. Okay, if the velocity is this way, then drag will be this way, and so on. Okay, and in addition to that, we also have a tension in this cable. Okay, this is what keeps the cable from not falling, basically. And that tension will be sort of, let's see, I would say tangent to the cable itself. And we're going to call this T, okay? And the tension has two components. It has a vertical component and it has a horizontal component. And as we discussed earlier, because the tension is tangent to the cable, then this angle is what we call theta, according to our previous definition of the angle theta. Okay? Now, let's see what we do with this. Well, because it's a free body diagram, we can say that the sum of forces acting in the x direction is going to be equal to 0, okay? Because remember, this is moving with a constant speed, so there's no horizontal acceleration and there's no vertical acceleration either, okay? And we have essentially two forces which are acting in the horizontal direction. So we have the horizontal component of tension, which is T sine theta, okay, minus the drag, let's call this capital D, and this is going to equal to 0. Okay, now let's expand this a bit further. So when we talk about aerodynamic drag, usually aerodynamic drag has this formula. So we have half, we have rho v squared s times cd. So let's try to break this down a bit. Now this rho refers to the density of the air, okay? And this is, well, just to keep things simple, let's call this a function of the shape. Okay, so this is a function of shape, okay? And this here is the, we would call this the wetted area of the cable. Okay, so in this case, we're looking at this section, this which has this length, and let's call this length maybe lowercase l multiplied by t. Okay, so this area is length times thickness, because if you think about it, if you look at the cable from the front, you're going to see a rectangle. Okay, so this surface area is actually the area of the rectangle. So this is L, the length of the cable, and the cable has a thickness T, so that's going to be L multiplied by T, essentially. Okay, and we're going to group some terms together here. So we have half rho, and then we have T, and then we have CD, and then we have L times V squared. Okay, and the reason I did it this way is because those are actually constants. And I'm going to call this this group of terms just K. Okay, so the drag acting on that section of the cable is going to be K multiplied by L V squared, like that. And then I will do the same thing with the vertical forces as well. But before that, I will rewrite this in a different way. So we have T sine theta minus drag, and instead of drag, we have K L V squared equals 0. And then we can rearrange this as T sine theta equals KLV squared. Okay, so let's call this one equation 1. Right. Now, from the vertical point of view, we also have just two forces, right? So we have the vertical component of tension, which is T cosine theta, and then we have minus mg, and this has to equal 0 as well. Now, this m deserves a bit of attention. So this is the mass of this section of the cable. So this will be called rho L multiplied by L. Okay, so this rho L, I'm going to call this the linear density of the cable. So this is the linear density of the cable, and this is the same everywhere because the question says that the cable is uniform. Okay, so if we rearrange this, we have that T cosine theta minus, and now instead of mg, I'm going to write the density of the cable times the length of the cable times g equals 0. So by rearranging, we have T cosine theta equals rho L times g. Okay, and the other equation, so this is equation 2, and the other equation was T sine theta equals, let's see, we have K L V squared. So we have K, we have L, and we have V squared. And this used to be equation 1. So what I'm going to do now is I'm going to divide the two equations by each other. Okay, so I'm going to do equation 1 divided by equation 2. Okay, which gives us that T sine theta over T cos theta equals KLV squared over rho L times LG. And you can see that this doesn't actually depend on the length of the cable, so that cancels out. And we have that this equals kv squared over the linear density of the cable multiplied by g. Okay, the t cancels out as well. And we end up with sine over cosine, which is tangent. So we end up with tan theta equals kv squared divided by the linear density of the cable times g. So let's take a closer look at this. This k we discussed earlier that it is a constant, okay? And so that's this k right here. And v is also constant, right? Because the helicopter is flying with a constant velocity. This is a constant because this is a material property of the cable, and of course g is constant. So this tells us that the right-hand side of the equation is constant. So I'm going to call it C maybe. So this will imply that tan theta is equal to a constant, which means that the angle theta is constant. So no matter where you are along the cable, this angle theta doesn't actually change. Okay, and of course in this diagram that I drew here, the angle theta does change. So if you're here, you have a different angle. So the only possible way in which this angle theta is constant, or in which the slope is constant, is if we're dealing with a straight line. Okay, so a straight line means the correct answer is either A or B, right? And everything else just goes away. And I think it's quite obvious that it cannot actually be A, because for it to be A, it means that this value here should be equal to 0, which is not the case. Okay, so tan theta is equal to some finite non-zero value, which means that the cable has a slope and the slope is constant, which ultimately means that the correct answer is B. So while flying with a constant velocity, the cable will assume this linear shape. Okay, and that's an analytical way of thinking about this problem, and that's the end of the question.